Hello, my name is Crislane and my partner is Bruna. We are chemical engineering students at Federal University of Rio Grande, and this is the Control and Automation of Chemical Process course. Today, we're gonna talk about the acceleration of the analog inputs of the Arduino Uno.
This project was based in the implementation of a code on the Arduino Uno that was able to accelerate the reading of analog inputs, increasing the clock frequency of the analog to digital converter through manipulations in the reading code in the Arduino IDE, giving us a time of response lower for the measured variable. The objective of this practice consisted of accelerating analog inputs of the Arduino and comparing variations of the data obtained with and without acceleration, using a LM35 temperature sensor to provide a voltage signal to the tests. First of all, we are going to explain some features of the microcontroller itself, as well as some of its parts and functions that are important to know for our practice. Microcontrollers are basically a small computer consisted of central process unit, data and program memory, clock system, input and output ports, and many peripherals. Essentially, they're a set of hardware with software, with the main advantage of these microcontrollers are do not have specific functions, which enables them to be programmed to perform different tasks according with the interest and creativity of the programmer. As a result, they become extremely useful in automation in general, especially for control and automation of industrial plants, for example. Microcontrollers are often found inside another device to be sold on the market. The Arduino Uno is one example of those platforms, which has an Atmel microcontroller named ATmega328B. Due to its simplicity, it's not necessary in having a great knowledge of electronics to use this platform. It can be easily handled for beginners or even for teaching automation purposes. In addition, it has relatively affordable prices compared to other devices on the market. Microcontrollers have also input and output ports, responsible for the communication with the outside world. These inputs can be digital, which are responsible for getting discrete data, or analogs that are able to acquire measurements continuous through the time, so they can take infinite values within a range. However, this analog signal must be converted into a compatible format in order to be recognized by the CPU of the microcontroller, which has a digital format. Analog to digital converters perform this conversion. This device has function to transform a continuous voltage range in discrete signal represented by binary numbers. This range is set according to the bit resolution of the converter. The resolution of Arduino Uno is 10 bits, which means that it can represent an analog signal of tension from 0 to 5 volts into a digital signal of binary values from 0 to 1023. The converter uses a function known as sample and hold, which is responsible for maintaining a stable voltage while the conversion occurs. The Arduino Uno uses a type of converter called analog to digital converter of successive approximations, which works coming always closer to the actual analog value by comparing to a reference voltage that is adjustable. This converter is controlled by a clock signal with a frequency of 128 kHz. This clock frequency can be changed by code modifications on the Arduino IDE, raising to a frequency of 1 MHz. By increasing the frequency, the analog to digital conversion becomes faster. As a result, the time of analog readings accelerate about 6 times faster than the original.
Now I'm going to talk about the materials and methods used in the development of our project. We used an Arduino Uno, laptop, USB cable to make the connection between the Arduino and the computer, an LM35 temperature sensor, and jumpers to make the connection between Arduino and the LM35 temperature sensor. In this image, you can see a virtual connection between Arduino and the LM35. After tests, this was our project. Initially, our project was consisted in the implementation of the program to accelerate the analog inputs of the Arduino. To do this, we first ran the test sketch to discover how long it would take to do an analog read. On the left side, you can see the test code. Then, the test code was modified to increase the frequency of the analog-digital converter of the Arduino from 128 kHz to 1 MHz, resulting in the acceleration of the analog read. This code can be seen on the right side of the screen. Now I'm going to talk about our results. After the implementation of the test code, it was found that the Arduino Uno took 12.461 seconds to make the reading of the analog inputs. This time was much smaller when we modified the code, increasing the frequency of the converter. With the frequency of 1 MHz, the Arduino took only 2.93 seconds to perform the reading of their analog inputs. At the end of our project, we decided to implement the code on the Arduino Nano and Arduino Mega to compare values. For the Arduino Nano, which has the same microcontroller of the Arduino Uno, the values were very close, with 12.351 seconds for the test code and 2.929 seconds for the fast code. In the Arduino Mega, the final code used to increase the frequency was not valid, since it has a different microcontroller. Thus, the reading was 12.481 for the two tests. Finally, we can conclude that the acceleration of the analog inputs is useful when the programmer wants a fast reading. However, this method has some disadvantages. For example, the resolution is affected when the frequency of the analog-digital converter is bigger than 200 kHz. Concluding, the objective of our project was achieved, since the fast code was 4 times faster than the test code. Thank you.